Hey guys, this is lesson 7. We will start root inspection. We will go to the next chapter, chapter 4. There are only 2 points that you need to know, you need to master. The third point that is in the book, you don't have to worry about that because it's for the decision mathematics 2 for the high level. So we will only cover these 2 points, and that is the use the order of the nodes to determine whether the graph is Eulerian or semi-Eulerian or neither. And the second point is to use the Chinese Postman algorithm to find out the shortest route in a network. So let's just go to do the first point first, and then we will move in the second half of the lesson to the second point. So first, let's just recall in our minds, what does it mean, what is a degree of a vertex? You should be able to answer this question on your own, that degree of the vertex is the number of the edges that are coming into that vertex. And obviously that can be either even number or it can be odd number. If it's an even number, then the vertex is called even or even degree, and then odd vertex is the vertex with the odd degree. The second question what we could ask and also recall from the previous lessons is what are the order and valency of a vertex and what is the difference between them. You can think a little bit, and you should also know that there is of course no difference. These are just the equivalent terms for the degree. So whether you say order or degree or valency, there is no difference in them. The meaning is the same. Now, also you can recall, or you should be able to recall and to know and to understand what is a connected graph. And the graph is connected if there is a path between any two vertices or any two nodes in them. Okay, so those are some basics that you will need to know if you want to understand what is the Eulerian graph. You might recall or you might know from the history of mathematics that Euler was a Swiss mathematician, and he heavily contributed to developing many branches of mathematics, one of them being calculus. So this Eulerian is from it comes from his name Euler. So we will call the graph Eulerian if the all vertices have the even degrees. We can also say the graph is traversable, okay, or Eulerian. Again, those are the two terms that you can interconnect or you can replace with each other. So when we look at this picture, then we have every single vertex here has an even degree. That's why this graph is obviously connected. You can see that because there is a path in between any of two vertices, and because every single vertex has an even degree, then we call this graph Eulerian. Now, there is something called semi-Eulerian if precisely 2 degrees are odd. That means if I have exactly 2 vertices that have odd degrees and the rest of them must be even. So for example, this could be the semi-Eulerian because you can see 1 and 1. So I have this one and this one are the odd ones, and I have precisely 2. It cannot be more than 2, it cannot be less than 2. Obviously, it is not possible to draw a graph with just one odd valency, with one odd degree. You can recall from handshaking lemma that the sum of the degrees is always even because it's 2 times the number of the edges. So it must be even. So that's why you cannot have one odd degree. So we can define the traversable graph. Traversable graph will be such graph where it's possible to go along or to travel along every edge exactly once while you start and finish at the same vertex. You can of course pass through the same vertex twice or more times, but through every single edge you can only go once. Okay, and there is the first note which says that Eulerian graph, that means it's the graph with all even degrees or all even vertices, is always traversable. These statements obviously can be proven, okay, but we're not going to prove it. You will just see it on the examples. Semi-Eulerian graph is semi-traversable. What does that mean? It means that the start and finish points will be two vertices with odd degrees. You can start at one odd degree, at one odd vertex, and finish at the other odd vertex. So Eulerian is traversable and semi-Eulerian is semi-traversable. You can only start and finish at the odd vertices. And then, of course, non-traversable graph is such graph that has more than two odd degrees. Eulerian and semi-Eulerian graphs can be drawn without removing your pen from the paper. Okay, I will show you, I think it's the next slide where we're going to discuss this. So you don't have to pick up the pen from the paper and you don't have to repeat any edge. So let's look at this note, how it works in practice. So for example, when you look at this graph has all even vertices. This one is, the degree is 2, this one is 4, this is 4, this is 4, this is 4, and this is 2. So based on what has been said on the previous slides or in a couple of minutes ago, this graph must be traversable. It's Eulerian graph because all degrees are even. That means I am able to start at one point, at any point you choose, and go back to the same point, covering every single edge exactly once. Okay, so we can, for example, I'm going to choose this one, and I'm going to go, and I'm not gonna take the pen from the paper or from the screen. Okay, I go like this, and I finish where I started. Okay, so this graph is Eulerian. Now, when you look at this one, you can also very quickly count the degrees of the vertices. So this is 2, 4, 4, 4, and 3, and 3. So this one is semi-Eulerian because it has two odd vertices. What that means is I can only start here and finish here, or other way around, if I want to cover every single edge exactly once. So I'm going to start at X, okay, and I will go and finish. For example, I can go this way. And I'm finishing there. Okay, so this one is a semi-Eulerian. But you have many roots, obviously. You don't only have one for each of the semi-Eulerian graphs. You can find your own. Then we have the next example. This one is 3, 3, 3, and 3, and this one is 4. So obviously, because I have more than two odd vertices, this one is neither Eulerian nor semi-Eulerian. That means I cannot, it's not traversable. That means I cannot start at one point and finish at the same point while covering each edge exactly once. Neither I can start and finish at another point because I have I have more than two odd vertices. And then the last one, the question can be, is this graph semi-Eulerian or Eulerian or neither? You might go back to the definition. What it says, the graph is Eulerian. For the graph to be Eulerian, the graph must be connected. So this is neither Eulerian nor semi-Eulerian because this graph is not connected at the first place. So let's do some examples together. Example 1 is very quick. You just need to verify that the graph is Eulerian. So here again, we go back to definitions. it's absolutely crucial that you need to understand the definition. Don't just remember it as monkey, but you need to understand what it says, and then you are able to recall it. So when you see Eulerian, in your head, in your mind, the light goes on and says, okay, Eulerian means every single vertex must be even. Okay, so first I'm verifying if it's even. I mean, if it's Eulerian, that means if every single vertex is even. So A is a degree 2, B is degree 4, C is degree 4, D is degree 2, E is 4, F is 4, and that's about it. So you can make the conclusion, all vertices have even degree. That means graph is Eulerian. And of course, you also know if graph is Eulerian, if graph is Eulerian, then it is also traversable. So the B question, you need to find the root. Again, you can find your own, but they give me the condition to start and finish at A. Okay, so I can go this way. I can go all around to F, then do the inner part, and then go back to A. Okay, so it can be A, B, C, D, E, F, B, C, E, F, and back to A. But you might have many alternatives here exist, okay? You can draw it differently. Many alternatives exist here. Good, so let's look at the second example. We need to find the root that traverses each arc of this graph just once. And this is a good information here. You may start and finish at the different points. That means most likely the graph is semi-Eulerian. We can verify it. A has the degree 2, B has a degree 3, C has a degree 3, D is 2, E is 4, and F is 2. So in here you can see exactly 2 vertices are odd. Exactly 2 vertices are odd. That means the graph is indeed semi-Eulerian graph. Semi-Eulerian graph, which means I can start at one odd vertex and finish at the other one. So in here I have an option start at B and finish at C, or the other way around. Finish C or C and then finish B. Okay, there is no other option. So because I know this, so I'll start here and then I finish at C. Okay, and you can find any option that you like, which will cover every single arc. So I will go this way: B A F E, B A F E, and then I will do this cycle, so C, D, E, and then I go back to B and F, B and C. So I started at B and I'm finishing at C, but every single edge was covered exactly once. So this is not difficult. Let's try to do the guided practice. So again, you have a chance to pause the video and check the answers, or you can do it along at the same time. So let's look at example 3. We have a connected graph. This is important information, and it has 5 nodes, 5 vertices. The orders are 4, 6, 3, P, and 2. Now, a case. Explain why. This is our favorite question. Explain why the graph cannot be Eulerian. Back in your mind, you can go to understanding what does it mean the graph is Eulerian. Eulerian graph has all vertices even. So can be, because Eulerian means every vertex or all vertices is even. But as I have number 3 there, which is obviously odd, so this graph can be Eulerian. Can be Eulerian. So for this one you would get a full mark because you need to explain it. It's not enough just to state that it's not Eulerian, whatever. It has to be clear. Your thought pattern must be clear. So the B case, again, explain why the graph must be semi-Eulerian. Well, you know that I cannot have one odd degree. The number of the odd degrees must be even. The number of the odd degrees must be even. You can see handshaking lemma that we mentioned a couple of minutes ago. Okay, so because I have already I have 4, 6, 3, P and 2, this and this must be odd, because I can't have only one odd number, one odd vertex. Can have only one odd vertex. Okay, so that means must be semi-Eulerian. C case, give the number of edges contained in this network. So again, you can go back to handshaking lemma, which says that the sum of the degrees is 2 times number of the edges, number of arcs. Okay, so I know the sum of the degrees here is 4 plus 6 plus 3 plus P plus 2 equals 2 times number of edges or arcs. So that means number of arcs or number of edges is, let me see, 10, 13, 15 plus P over 2. Or P plus 15 over 2. And then the last one, the D case, we need to draw a graph with 2 nodes that is neither Eulerian nor semi-Eulerian. Well, then it's very quick and very easy, because if you do not want the graph to be Eulerian, neither semi-Eulerian, just draw the graph that is not connected. And because you have 2 nodes, then this will be first one and this will be the second one. And this is not connected, that's why it cannot be Eulerian, neither semi-Eulerian. Not connected, can be Eulerian, semi-Eulerian. So the next example, example 4, you are given the adjacency matrix. You can recall what does that record. Adjacency matrix record the number of the edges between 2 arcs. So for example, between A and B, there is 1 arc or 1 edge. And now we need to analyze this matrix and answer the questions. So A asks us to state whether the graph is connected, and you have to offer the reasons. So you may recall, and you need to know, the graph is connected if there exists a path between any of the 2 nodes or any of 2 vertices. This takes a little bit of practice, but you can easily see, for example, I'm going to take A, And from A I can get to B and I can get to C. Okay, that doesn't have to be the direct connection to D or E, but I can check if there is if the path continues from these two vertices. So for example, from A to B, and then from B I can only go back to A, or I can go to C, that's fine. But then once I'm in a C vertex, I can only go back to A and B. There are no connections to D and E. That's why the graph cannot be connected, because I cannot get from A to D or E. Okay, so from A to D or E, there is no path. That means the graph is not connected. But there are more. Graph is not connected. But there are actually more you can also discover on your own, different cases. For example, you cannot get from B or C, you cannot get to D or E. Okay, so any of these you're going to state as your reason is enough, because it's fine when you find one. So then the B case, state with reasons again. You need to offer the reasons whether the graph is Eulerian, semi-Eulerian, or neither. So now you should clearly and immediately say neither, because for the graph to be Eulerian or semi-Eulerian, it must be connected. So because it's not connected. And now the C case, we can draw it. Well, because we analyzed at the beginning that from A I can only get to B and C, and then I have to go back. So A, B, and C, because there are no connections to D and E, and I know that it's not connected, then it's easy to draw it. You can also see from D to E there is one connection, and from E to D is also one connection, one edge, right? So there are zero connections to A, B, C from both of these vertices. That's why that's disconnected. It's not connected. And one more, example 5. Again, we have an adjacency matrix for a connected graph. In this case, it says it's connected already, so I don't have to worry about that. And I have to determine whether the graph is Eulerian, semi-Eulerian, or neither, and again, give the reasons for your answers. Okay. Now, you can see that A vertex has the order 2, because there is one edge going to B and one edge going to E. B vertex has the order 2, C vertex has the order 2, D vertex has order 4, and E vertex has order 4 again. Okay, so what does this tell you? Every single vertex is even, so all vertices are even. That means all vertices are even. That means graph is Eulerian. If you want to succeed in these kind of questions, it's absolutely crucial that you are confident and you understand the definitions. You are fluent with them. You can exchange them. What you see when you see the word Eulerian, your mind understands immediately that means all vertices are even. It is absolutely crucial that you need to understand and you need to be fluent with the vocabulary. So we will look at the next problem that is called 7 Bridges of Konigsberg. It's about a city in Russia, and this city has some islands or some neighborhoods in the city that are connected by the bridges going over the river. And the question was if we can find such a walk throughout the city that would cross every single bridge exactly once and only once. And Euler realized that this problem can be simplified and represented by the graph. And he had redrawn the picture, the scale of the city, the map of the city, in such a way that he represented the districts by the nodes, by the vertices, and the bridges represented the arcs. When you look at that and you find out that the degree of the degree of each arc, this one is 3, this one is 3, this one is 5, and this one is 3, you can notice that every single degree is odd. And what Euler has noticed that unless each node has an even degree, then such walk or such route cannot be found. So this problem is unsolvable because there are the degrees of every single vertex are odd. In the second part of the lesson, we will look at the new algorithm that is called Chinese Postman algorithm or route inspection. This algorithm is used to find the shortest route. This is important. But in addition, the route in such a way that traverses every arc at least once and returns to the starting point. Okay, so exactly what we were talking about when we were looking at the Eulerian and semi-Eulerian graph, but in this way we're going to introduce the algorithm that finds such a shortest route. So the algorithm works like this. You need to identify in the first step the vertices with the odd degree. Then it's going to get a little complicated before you will see how it works, but you need to consider all possible complete pairings of these vertices. Then you select the complete pairing that has the least sum and add a repeat of the arcs indicated by this pairing to the network. So rather than just reading through the algorithm itself, I would prefer if you see it how it really works. When you will be discussing or following the route inspection or Chinese Postman with the Chinese Postman algorithm, you will always encounter 3 basic options. The options that are more difficult are not in your syllabus, they are for decision mathematics too. So the easiest option is when you have all vertices with an even degree, because then you know that this graph is Eulerian, and that means the network is traversable. Thus the length of the shortest route that is passing through every single arc will be equal to the weight of the network. So it is enough when you will just add the weight of every single arc. So we obviously will have many different shortest routes, but all of them will have the same minimum length. Let's look at the question example 6. In this diagram there is a network of some biking routes. The number on each edge is the length of the trail in meters. And Hannah starts at A, vertex A, and traverses every trail on the network and then returns to A. Okay? And you are asked to find out the length of the shortest path she could take. Well, you can notice that A has the vertex 2, degree 2, vertex B has degree 2, E has degree 4, C and D have degree 2. So all vertices even. tell your brain, tell your mind that the graph is Eulerian, and this is the option 1. That means the shortest route is the sum or is the weight of the whole network, right? So the shortest route is the weight of the network. That means I can just, or the sum of the weights of edges, you can say. Weights of edges. So in this case, it would be 11 plus 10 plus 7 plus 9 plus 8 plus 12. So the shortest possible route, the length, the shortest route is 57 meters long. They didn't ask us to state which route, so it's enough you are finished here because you just stated you answered the question. They didn't ask you to specify which route she could have taken. So option 2 is when the graph has exactly 2 vertices that are odd. You know that it's a semi-Eulerian graph, that means semi-traversable. That means you can start at one odd vertex and finish at the other odd vertex. But in this case, you need to repeat the shortest path between these 2 vertices. If you want to make it traversable, then you need to repeat this path between the shortest path between these 2 odd vertices. Okay, then you will add it to the network. It might seem complicated when you read it because you are not able to imagine yet what it actually takes to do, but I will show you in the next example. What is important to notice is then the shortest route or the length of the shortest route will be equal to the weight of the modified network. So you will just take the weight of the original network and you will add to it those 2 arcs or those arcs that need to be repeated. Okay, very, very important note, and please pay attention to this one. The shortest route, this is important, between the adjacent odd vertices does not have to be the direct link between them. What that means is, when you look at this example, for example, if I want to go, I'm going to call them A, B, and C. A to B, the length is 7. But it doesn't mean because it's the direct link that it's also the shortest link, because I can go to C first and then to B, and that will be only 5. Okay, so the shortest doesn't mean the direct one. It doesn't have to be true. In most cases, obviously it is, but in some cases it's not true. Okay, I mean on the graph. So let's look at the example 7. In this case, the diagram shows a network of the undersea cables. Okay, the number on each arc is the length in kilometers. Dive needs to inspect the cables and needs to find the route of minimum length that traverses every cable and starts and finishes at vertex S. Okay, so where is the vertex S? Okay, so I am starting and finishing here. And we need to stay the cables that will need to be traversed twice and stay the minimum length of the diver's route. So now let's start with finding out the order of the vertices. So T has the order 3, R is 2, Q is 3, P is 2, S is 4, and U is 2. So when you look at this, you can see it's a semi-Eulerian graph. That means you cannot start and finish at the same vertex S, but you can make the graph. So first thing, you need to make the graph Eulerian. How? By repeating the shortest route between the odd vertices. That means I have the odd vertices are which one? Q and T. I need to find the shortest route. Find the shortest route between these two vertices. Shortest route between them. Repeat and add it to the network. Repeat it and add to network. So now when you look at it, from Q to T, you have several options. I could take this route, but that would be, the length would be 15. I can take the direct one, 5, 4, the length would be 9. But don't forget to check the other ones, because for example, 6 plus 2, it's 8, plus 4 is 12. So in this case, the 9, or then you can also do 6, 2, and then 3 and 2, that would be 13. So in this case, really the direct one is the shortest one. So I need to repeat, so QT, QS, and ST. Repeat these arcs. Repeat these arcs. And this will make the graph traversable. Let me change, I'm going to delete this, what I sketched here. Okay, so I'm going to repeat this now. This was 4, this was 2. So I am repeating this one, and I am repeating this one. So these two, so Q and S need to be repeated. So this is the A case, and then the B case stay the minimum length of the driver's route. Minimum would be then the original weight 37 plus the one I repeated. That means plus 9 in this case. So I have 46 kilometer is the shortest route possible. Shortest which start and finish at S. Starts and finishes. The most complex option is option number 3, when you have more than 2 vertices with the odd degrees, but you don't have to worry, because for you the maximum number of the odd vertices or odd the vertices with odd degrees will be 4. Okay, there is no more. So in this case, we need to consider all possible pairings of the odd vertices, and if you have 4 of them, then it's not very difficult to find every single combination. So let's look at example 8. We need to solve the Chinese Postman problem. If you see something like this, that means you are looking for the shortest route that starts at return, in this case vertex A. Okay, so this means the same as to find the shortest route. So let's look at the vertices and their degrees. That's where we always start. So I have degree 4, degree 3, 3, 3, and 3. So this is not Eulerian, neither semi-Eulerian, okay? Not Eulerian yet. Eulerian, not semi-Eulerian. but I can make it to be that way. Okay, so I have A, B, C, D are my odd vertices. That means these are the vertices that I need to create the pairings from, because you can only start and finish at the odd vertex. So in this case, I have options A, B, and then C, D, or another option will be A, C, and B with D, or next option is A goes with D and B goes with C. Okay, so I have option 1, option 2, and option 3. So what does that mean? I need to find out the shortest possible combination. So I'm going from AB. The shortest route from AB is 8. It's the direct link in this case. From CD, again, you can see it's 9, but you can also go CED, but in this case it would be 11, so the shortest one would be really 9. So in this case it gives me 17. Now from A to C, 5 plus 7 is 12, 7 plus 9 is 16, 8 plus 6 is 14. So the shortest one really is the direct one. In this case goes through E, so 12. This is A, E, C, plus, and B to D, the shortest one would be 10. So again, B, E, D. Okay, so I would have 22. And then I have AD. A to D, the shortest one is direct link, 7. Not always the case. And then B and C is the 6 is the shortest one. Again, it's the direct link. So together 13. So now you are able to choose which one is the shortest one. Obviously, this one is the shortest one. That means I need to repeat and add to the network, repeat AD and BC. And I'm going to add it to the network. So AD, I'm going like this, and then BC, I'm going like this. And once I repeat it, then I can find the possible route that finish and start and finish at A, because suddenly I have all vertices became even. This is 4, this is 4, this is 4, and this is 4. So that now the graph is Eulerian, that means it's traversable. Now they ask me to, they didn't ask me, but when you are solving the Chinese Postman problem or finding the shortest route, obviously we need to state the shortest route. So shortest route length, shortest route length would be then original length was 52, and then you edit 13 extra. So should be 65, either meters, kilometers, depends on the unit. And then possible, you can find one. This one has many solutions, but each of them will have the same length, which will be the shortest, the minimum. So possible route can be, let me take the different color. So possible route can be, I have to start at A, okay? So I can do A, B, C, E, B. Then I can go through here, but I need to record it because I will get lost. So A, B, C, E, then go B, C again. Then I can continue. I can go to D, I can go to A, so D, A, then E, D, and A again, E, D, and A again. But this is just one of the options, okay? Obviously, you can find many different routes. So now these points should be much clearer what they mean, okay? What they mean by considering all possible complete pairings, what does it mean to select the pairing with the least sum, and add and repeat the arcs indicated by this pairing. Now it should be understood. So let's look at the guided practice for this part, for the shortest route and Chinese Postman algorithm. I think I prepared 2 examples for you. Feel free to pause the video and check the answer, or feel free to follow, depends, and it's up to you. So in example 9, we have to solve the route inspection problem for the given network N. Important point is you always have to make your method and working clear. If it's very chaotic, if your thoughts cannot be read from the paper, you are risking to lose the marks. And in this case, they also ask us to state a shortest route and find its length. So where we start always is with finding the degree of every single vertex and identify the vertices that are odd. So in this case, we will have odd vertices A, because it has degree 3, then B 3, then we have C is also 3, and D is 4, E is 2, F is 3, and G is 2. So I have 4 vertices that are odd. That means I have to find out the shortest routes. I have to find out the combinations between A, B, C, F. So create the combinations. It must be either A, B, C, F. Then you can find out the shortest route from A to B is the direct link, 48. But from C to F, I don't have a direct link, but you have 2 options. You can either go C, D, E, F, or you can go C, D, F. So you have 48 plus 160, so that's 208. The next combination would be A, C, and B, F. From A to C, the shortest one is the direct one, 117. And from B to F, the direct one is also the shortest one, that's 63. So together 180. Then I have last combination, AF and BC. From A to F, I can go the shortest way, I can go through B, 48 plus 63 is 111. And B to C, the shortest one that I can go through is to go through G. So B, G, C gives me 140, B, G, C. So together it's 251. So once you identify this, obviously you see the shortest one is 180. That means I'm going to add AC and BF to my network. Once you add it, this network became Eulerian because every single vertex is now even. And also you can find out the shortest one because you repeated the arcs that were the shortest. So length of the route would be the original weight is 802 and the one that you repeated is 180. So 982 is the shortest possible one. If you want to find out one possible route that has this, then you can create your own, but the example starting from A and coming back to A would be the one that is given here. So in example 10, we are again given some network. In the A case, they first ask us to describe a practical problem that could be modeled by this network. You can come up with your own ideas. One of the options might be that, let's say, at point A is a post office, and then I have several places, either companies or houses, that I need to deliver the packages to, and I need to find out the shortest possible route. That could be one of them. And then in the B case, we need to use the root inspection algorithm or Chinese Postman algorithm to find out which paths needs to be traversed twice. Because you can notice immediately, for example, the vertex is odd vertex. So it's not a Eulerian graph. That means some of the parts of the network must be repeated. So let's look at the odd nodes first, identify them. A has degree 3, then B has degree, where is the B? 3 as well, then D has 3, as I said before, and F. That will help you to come up with the possible pairings, the shortest route. So create your own. It might be ABDF. From A to B, you have several options how to get there. Either you can go through F, what the distance would be then 33, or you can go through E, and then the distance would be 32. So consider the shortest one, then it's obviously via E. And then DF, the shortest one, is a direct link, what is 9 here. So 41. Then next combination is AD and BF. AD is 26, that's the direct link, and B and F is also the direct link, so 26 and 15 is also 41. And then the last combination is AFBD. A to F is 18, and B to D is, where is the D? B to D, the shortest one is 15 plus 9, what is 24. But you have to check all possible routes and to find the shortest one. So in this case, it's 42. Okay, so you can either repeat A, E, EB, and DF. That would be for this option, because AB you can go to AEB. That's why you see AE and EB and then DF. Or another option is you can repeat DAD and BF, because both of them are the shortest one here. Okay, so they have the same length, so you can choose which one you want to. That's why you can state in the C case that the answer to part B is not unique, and the reason is exactly here, because I have two options with the same length, so I can choose which one I will repeat. Now for the D case, then it's easy because I know how long is the part that need to be repeated. That's 41 meters or kilometers. And the original weight of the network was not given, but obviously you can, if it's not given, you can easily count it. Just add up all the weights of every single arc. That should be 258, and then you repeat 41. So together the shortest route possible is 299. Okay, they didn't ask you to find the route, so this should be fine for now. But there is one more part to this example we're going to look at, and that's the part E. If it's permitted to start and finish at two different points, two distinct vertices, then we need to find which two vertices should be chosen to minimize the length of the route. As you know, that A, B, D, F were the ones that were odd. I need to choose the combination or two of them that will give me the shortest arc. So in this case, the shortest arc would be DF. So if I only repeat D and F and I would add it there, then it would give me the option that DF is repeated. That means I can either start at A and finish at B, or start at B and finish at A. And then in that case, you would have the shortest route possible. In this case would be 258 was the original one, original network, and you would repeat only 9. So the shortest route possible would be 267 units, kilometers, meters, or whatever. But in that case, you are not going to start and finish at the same place. You are going to start and finish at two places. In this case, it would be A and B. And this would be all for today. We have covered section 4a and section 4b. If you finished all guided practice, you have some questions, then please come and clarify it at the tutorials. In the same time, you can start practicing these questions that we will focus on in tutorials, while I can help you to clarify your doubts and explain you your questions. Don't forget, the solutions are at the end of the book, and also the detailed solutions are on this website together with the templates needed. And so I thank you for your time and your will to work hard, and I hope to see you at the tutorials. Bye-bye.